Charlotte is the lead application engineer at ANSYS Inc., supporting the high-frequency product applications. She specializes in HFSS product, which is an FEM, electromagnetic simulation software code for RF and microwave devices. Prior to working at ANSYS, she worked at Radio Frequency Systems as a filter design engineer, where she designed, built, and tested prototypes of various cellular band pass filters. Currently, she's the IEEE Connecticut Section Chair for the MTTS, ATS, UFFC, and WIE societies, and IEEE Region 1 Public Visibility Chair. She's also the Technical Program Co-Chair for the 2016 IEEE R1, R2 WIE Forum, and Charlotte received her BS in Electrical Engineering from Rutgers and her MS and PhD in Electrical Engineering at NJIT, which is the New Jersey Institute of Technology. So I'm very pleased to introduce and welcome Dr. Blair. Charlotte.
Thank you. Thank you, Tony. And as I promised some of these folks here in the room here, we're going to start with Maxwell's equations down much. So today we're going to talk about some of the ANSYS electronic tools. We're looking at the high-frequency and multi-physics applications. Okay. So this is the meeting notice. So this is what brought you here, and we're going to be looking at, different applications of the ANSYS tool sets. Okay, so I know that several folks here are electrical engineers. Let me ask you, who is a mechanical engineer? We have mechanical, or are we all electrical here? All electrical? Okay. And how many have had exposure to the ANSYS electromagnetics HFSS tool, or any of the ANSYS electrical tools? Okay. How many people use ANSYS mechanical or thermal? Okay. All right. All right. So that'll just give me an idea of where I should start. So today I'm going to just give you an introduction of, I'll give you a high-level introduction of our tools and what we offer in simulation. I'll give you an example of areas where we fit in, and by business initiatives as well as applications. Now, when I come into Burns Engineering, I actually Googled you guys on the internet, and I see you you participate in many industries. So we can't say we are just here for smart devices for IoT. I can't say we're just doing communications. I can't say we're doing mil, aero. We can't do, aviation. I did see a lot of transportation. We have power and energy applications. We have biomedical. Does anybody do any biomedical implant projects here? Okay. Just so you know that we even have human body models within our product. So if you were ever interested in designing the smartwatch and you wanted to actually see what was going on, or how, 10 years ago we were interested in how the electric fields penetrated the head. Well, you can now take a look and see what the fields are from the smartphones that they penetrate into your hand. And so we'll also look at other different applications. When we speak electrical engineering, I know a lot of folks here are from the Power Engineering Society side. We also have what we call the high-frequency side, and we have the low-frequency side. So if you were back in your, when you first took your first class of electromagnetics before you were introduced into Maxwell's equations, right, you say, oh, well, let's look at the DC. We'll make some assumptions at DC. We're going to look at electrostatics, and then maybe we'll look at time-varying scenarios using the governing Maxwell equations. So we will be looking at those set of problems both in the high frequency and the low frequency for power analysis, signal integrity purposes, and then we couple all that information to also the ANSYS mechanical, thermal, and structural, as well as fluid type of applications. So not only are we strictly siloed into electrical engineering, we share our information with our mechanical, thermal, structural, or even our fluids application. So we take care of the coupling, very non-trivial type of interface between, say, electrical and mechanical. And then I'll stop talking, and then you can answer questions. So for those on the webinar, if you don't mind holding your questions or placing them in the chat window, and then we can answer the questions at the end. Okay, so I'm hesitating to talk because proceeding with what I had planned. And since the majority of folks have not used the ANSYS HFSS tool or the electromagnetic simulation tool, I'm going to just bring it up one level. So I'm going to, if you do have questions, I'm going to try to answer them. And for those in the room, if you have a question, just stop me at this point, because I don't want to just be talking and everybody's just, knocking their heads. So what I have here is plots of the electric fields of different type of devices. Now, ANSYS is a simulation house, and we use simulation to characterize devices and or systems for your product design. For your product design that you cannot probably physically build or want to build every test scenario. And this is when you would reach for our simulation tools. So the most simplest, or one of the simplest forms is if you open up any electronics, you're going to see a printed circuit board. And one of the important components of this is to take a look at the via. The signal comes in through the via and it's transported along the microstrip trace, whether it's, on the board or embedded in between boards. So what you see here in the colored plot, red is being the hottest, blue being hardly any field. This is a plot of the electric field strength. Okay, we want to make sure that where you intend to put signals or where you want the signal to propagate, you want to see red. And where you intend it to be ground or you want no radiation, you want that to be blue. And we look, HFSS is an electromagnetic simulation tool that is looking at the electric field, the gradient of the electric field, and then we calculate the magnetic field. Okay. We also have a Maxwell tool that calculates the magnetic field, and then we calculate the electric field. So think of this as, if you're doing board type of applications and you're interested in the electric field, you're interested how the signal is propagated, you want to look for our HFSS tool. We look at, if you're looking at wireless power transfer, you're looking at your RFID applications, or even some of these smart sensors, you may want to look at our Maxwell tool where we're looking at the magnetic field. Now, as you recall, the electric field and the magnetic fields are coupled together. And depending on the scenario and what you're focusing on would determine which tool you're going to look at. So not only can we look at, planar type of applications, board applications, we also look at waveguide type of application, something that's very generic. Here it happens to be a 5-pole filter. I will be very careful because I know we have an expert in the room on filters. And we have a cavity filter here that also uses dielectric resonators as well. So the coaxial feed, and you will want to look at how the fields penetrate in that cavity. The penetration here depends on those openings between those cavities, and with the simulation tool, you can visualize it, you can see it. It's no longer going into the lab and saying, this is black magic. I don't know how to tune this thing, but I know that if I do this, this, and this, I'll get some sort of response. You can actually see where the electric field and magnetic fields are propagating. And it will show you as best as to what you put into the simulation tool, as well as what geometry you're putting in there. So besides, boards and waveguide type of devices, we can also say, hey, nowadays we're saying, I need connection. We were having problems with the Wi-Fi here, right? Well, maybe we weren't connected. And if you were at I'm North Jersey, so say, if you wanted to go to the Yankee game and you're up in one of those tiers and you're not getting reception, yes, you're going to be upset because you're not getting reception. And maybe it's because your antenna array is not focusing your beam in the direction of where you're sitting to a transmit. Okay, and here you can see that you want in the direction that you're pointing your antenna to be read. Okay, so we can also characterize boards that have antenna elements on it as well as active devices on it. So we're not just looking at, passive devices. If you have ASICs or any chips that you want to put on your board, we can include that in our electromagnetic simulation. Say, why do you want that? Well, again, you're looking at the electric field plot and you want to see where the current is going. Anything that populates the board is going to get hot, and because we're ANSYS, we can also look at hot spots. We want to see where power, voltages, and currents are going. Because this element, or this device, can be put on a drone, right? So, okay, well, I have a picture of a drone here. So we can place that element on some sort of platform, in some sort of packaging. And any of the elements that we design using our tools, you want to see what the effects of the packaging is. You want to see the effects of those blades moving around. So you need to couple the electromagnetic with the mechanical, the structural, the changing of the propellers here, and the orientation of the device to your transmitter, your receive element. And again, here you have your antenna element, and here you can see what the current or the fields are being distributed on the platform. We take that one step further because we are looking at IoT, right? We're looking at smart devices and gadgets. Nothing stops us to take our antenna element and putting it in a manufacturing area, right? Because we just now love to collect data, right? So if I'm in some sort of factory and I need to get in touch with so-and-so, we're going to do it through Wi-Fi. So we're going to put antenna, repeaters in several areas. And again, going back to your undergraduate classes, it all matters how your wave or your field is propagating, and as soon as it hits a boundary condition where it is a conductor, right? So thank God this place, on the 6th floor here, this beautiful building, you must have lots of steel and everything. So all the signals are bouncing off anything that's metallic. So you can see that wireless says, oh, if I see anything that's conductive, I'm going to be reflected and I'm going to change my path. So the one thing that's important, we have wireless channels. Great for, I don't have to lay down cable and connectors. I don't have to lay down or fibers because I don't have a channel. The entire air set is a channel. That's great in one respect, but on the other hand, that's a huge negative, especially when you're inside a building, and every time I hit something that is conductive or of a different material property, of a different permittivity, I'm going to have reflections and transmission. So you may have heard, the multipath and the fading. That is all a function of the wireless signal hitting some sort of boundary condition. And with our tools, we're going to calculate all that. So we can go something as simple as a component all the way to a device and packaging, all the way to an entire system. Okay, so again here, red being hottest and, blue being almost no field. So you can see we have a very large span of use models within the electromagnetics. So we can do antennas. These are just some areas where we excel in. We can do installed antenna performance. Non-trivial. The platform does change your antenna pattern. You can create an antenna and design an antenna and say, yes, it's going to work. But as soon as you put it in the packaging, its module is going to make a difference right? 10 years ago, what was our antenna gate? That's the best example there is. Oh, nowadays, you know, the major focus is if you're going to do sensors on the autonomous cars, that's a big application. Traditional RF and microwave, the filter design, satellite communications, putting arrays up on the up in space. Now we're looking at power electronics, right? We want data, we want all this functionality, so we need all these boards populated not only with traces but with components, but they need to be powered up. And so we have tools that can simulate the entire board as it is active in either some on or off state. We can take a look at any interference, right? We have many devices that are on Wi-Fi. I was just talking about electromagnetics, right? You know, the field propagating, it's bouncing off the walls here. But if I have, everybody has a cell phone, you have your smartphone, you have repeaters up here, and so all of these are, yes, at different frequencies, but at some frequencies the fields will couple together, and so we can look at radio RFI type of applications where we have more than one transmitter, so we can do a scenario set. We can look, you know, at the electronics on a board. They process information, you know, and I'm going to show my age here because, so when I went to school, you had the option of being analog or digital. Right, you could go into RF and microwaves, which is analog, or back then digital was the big thing. You know, you wanted to do computers, and the real world in itself is analog. Okay, we do not see just ones and zeros. So in our signal integrity applications, they want to see ones and zeros. So you're going to take an analog signal and you're going to try to discretize it into some levels of ones and zeros, and you want to take a look at, you know, is this signal one or not? And so you're looking at eye patterns. So you're looking at the integrity of bits going through your system. So we have tools, again, electromagnetic space, that will also look at your signals, your signal integrity. And then most recently you have, you know, signals, you have all these ASICs, again, they're powering up. Heat loss, heat junctions, right? Heat sinks. This is very important for power integrity type of applications. Where are you going to cool it? You're going to put it in some sort of cabinet. You're going to mass it somewhere. So how are you going to affect the cooling of these devices? And if you have a radiator in there, or if it's for a space application. So you would need to pull for something like a fluid analysis. So you're going to be coupling electromagnetics with fluid analysis. Again, for low frequency, again, electrostatics, if you're looking straight DC power, you know, for power electronics, you know, looking at the magnetic fields, we have low frequency solvers, and again, the DC for electric motors. So we have these products. So how do we align ourselves with what is going on in industry? If we look at industry and we're looking at trends, the trends that I see today is probably the same trend that, you know, that I've seen 10 years ago, 20 years ago. Okay, so to tell you the truth, it's really nothing new because we're all going to say, you know, I want my cell phone, I want my device, I want my chip to be smaller. I want it to be smaller, okay, after this. That is always the mantra of any manufacturer. Okay. And you want to put a lot of functionality in that chip. Why? Because everybody wants to stay connected. And I want to take really great photos, so I need images, so I need a lot of bits processing that. I want to make sure I can make a phone call and receive a phone call. I want to make sure I can locate and get directions. So I need all this functionality in a very small footprint. So that's going to drive the miniaturization of component parts. That's going to affect the infrastructure, right? Right now, you heard 3G, 4G, 5G. We have no idea what G we're going to be in, or if it's really, you know, 5G. I don't even think we're really at 4G, but so we haven't even decided what we're going to do really for 5G. So we have to look at the infrastructure because those signals, those air interfaces are going to drive the electronics that we have to put on this board so that we can communicate. So you can see that where I'm trying to get at is that we're getting into this very vicious cycle. And so with all of these functionalities and everything on this board, we need to power it up. And right? And so we know as engineers, we look at every single scenario. So therefore, we should not have seen that battery, heating up and burning up, right? We should have known that. We should have done a simulation on it that said, when have I had a spike in here? Even though I'm powering up, we need to be looking at everything. So all these test cases can be done in your simulator. And then we have simulation tools that takes all this data so that I can interpolate. Because I like data, right? I need to know, where I'm going to, and I know when I go into the target, they're going to say, hey, this is on sale. I saw you bought that last week. So we need embedded, software in all these devices. So you can see, this is a vicious cycle. I was giving you information on stuff that I see today, but this happened like 10 years ago. The cell phone before was, this big rectangular box, and then you had your pager. But we're always going into this vicious cycle. This is where the trends are. This is what the industry is asking of us. And so how does ANSYS align ourselves to all this? Okay? And so if we look at we'll go back to here. If we look at the chip manufacturer, and I just noticed something here. If we look at the chip manufacturer here, I should have, so did these slides last night. I should have replaced that with Qualcomm, right? Because Qualcomm bought NXP. So we know that these chip manufacturers, right, they're coming out with these chips, mixed signals, right, because they're both analog and digital. They have all these functionality on it. So these guys are saying, yeah, I need to do this with your tools. This is what you need to add on as a feature. So that's going to drive our feature list or our simulation tools list. We're going to look at the networking, folks, because, for instance, we have Alcatel-Lucent here. We have the chips here. These chips have to have some air interface here. They're going to have to say, you make sure that you have the speech, your antenna mass and all the filters and all the drivers and matching circuitry is in what's going to actually pass signals around. We want to make sure that all that information that's being gathered, like with NVIDIA, they have for their processors, we can take a look at an image, process it, and tell you what it is. Okay. So all of these folks need some sort of simulation tool. And ANSYS here, we bring all of these tool sets, these simulation tool sets together and integrate it. And so we use many of our different silos of electrical, thermal, and structural and data collection together. So let me take a look at a few of the initiatives that we have. So on the business side of things, your executive management is always saying, take this product, optimize it for power, performance, and cost. Everything is cost effectiveness, right? Bring down the cost and, make it as cheaply as possible. But you want it to be reliable. You want your network to be reliable. Make sure that we have signal and power integrity on our components. Make sure that if I drop my cell phone, that the LCD is not going to break. Make sure that if I happen to put my watch on the shower, that I'm not at 30 degrees, so that the water is going into my unit. So, these are things that we're looking at. Not just the electrical performance, but it has to perform in the environment, in its operating environment. So again, getting back to NVIDIA, right? Not NVIDIA, Qualcomm here, right? We have all this multifunctionality here, and they're making the chips. They need to look at the cost, they need to look at the performance, they need to look at the power. They're going to use the ANSYS several different product applications in order to do this. So they're in charge of miniaturizing. If your customers or you're contracted out to do work on designing chips or transistors and packaging it, we have simulation tools targeted just for semiconductors. Okay. So this, we have totem and red hawk. That's just like in the board. So if you translate, you have a board, you have a certain stack of, whether it's silicon or GAN. And you have certain traces on there. And you want to see how the signal is propagating through that substrate or through that chip level. We have, after you create the chip, then you're going to need to connect to it. Whether you're going to use wire bonds or you're going to have some sort of leads that are coming out of your chip, you're going to need to package it up. And maybe you're going to need to know what is the R, L, C, or G, right? You remember resistance, inductance, or capacitance. And so we would look at a cross-section of that part, and we would use our Q3D extractor here. Or if you're looking, after you made the package, and you want to take that chip that has, with an antenna, put it on a package, and you want to put it into some other package, you want to see how that antenna is going to perform. You want to look at what is that antenna pattern. You want to make sure that your red that you see for the field that's radiating out is in all planes, so that you don't have to be pointed directly towards the window if you're on the top floor of the hotel, so that you can get some reception. But you want it to be omnidirectional. You want to make sure that you're not going to distort the field pattern when you put it on some sort of platform. And again, you want to collect all that data so that you can provide some intelligent information to you as a consumer. So if I look, and again, like I said, I'm trying to keep this as top level as possible. So if we create the antenna here and we place it on some platform, maybe this is the HVAC on the manufacturing floor, and we want to see how does that impede the radiation, right? As soon as I put in the antenna on anything that's metal, right, it's going to reflect. I'm going to ground it. I am going to create some sort of ground, and ground matters, right? Ground current matters, and I'm going to distort this antenna. If I had said, this is going to be an antenna that's radiating in all directions, and I failed to put the fact that I'm going to actually mount it on something that's metal, I'm going to distort that radiation pattern. So the platform does matter. I could have, it probably is not best practices to design an antenna in isolation. And then I'm going to put this in an entire system. So whether I put it singularly on a platform, or if I put it, this one is supposed to be the ear, or whether I implant it in the human body, that's supposed to be a hearing aid there. You want to see how the fields are penetrating into the platform, whether it's metal or dielectric, right? How do the fields penetrate into your brain or, into a part of your arm? And you want to take a look at, what the field pattern is. What is the radiation that's being emitted out of that device? Okay. So we can do from the component level all the way up to the system and characterize the field patterns or the transmission to doing a system type of application. Let's see. These are just, again, just emphasizing, we can take a look, it's not going to be a simple board. You're going to have a very complex looking board. It's going to have many traces. It's going to have chips on it. It's going to have wire bonds. It's going to have vias on there. We can characterize the path of that signal. We can look at the eye pattern as that signal propagates on that very complex board. And we can take a look at that board as we engulf it into non-air type of materials. Okay. Here's the field pattern of a smartwatch, right? So that has functionalities of not only, a phone functionality, it does heart monitoring, it does, fitness levels. A lot of people use it for running. So most of these functions are also dependent on the environment, on its platform. Some people may be very sweaty. Some people may be very fit, so it's perhaps, they have a very muscular arm. Or we're using these Fitbits and smartphones so that we can start to drop some weight, so we have more fat layers than most, right? So each of that is a boundary condition. Each of those scenarios changes your field pattern of how much is penetrating. And so the folks that are creating this smartwatch, they need to know this stuff. They need to know what will happen if there's a lot of sweat, if there's a lot of water absorption, if there's a lot of different, body fluids that are being passed. And they're going to need to know also, hey, if I have this part, not only is it just static, and I can take a look at the radiation pattern, what if it drops? What if it falls? What if it cracks? Okay, where is it going to break? And that's something that we can take a look at with our structural as well as our thermal. So you're going to have to do shock and vibration and thermal testing. You have to test out the part, but like I said, you can't always test out every single scenario, especially on a manufacturing floor. You're going to go to that specific area and test out the wireless signal, the strength of the signal in every single room. Maybe, a couple of years ago, that was the way we had to do things. You place a transmit down and you see if you have your reception in the other room. But now we have simulation softwares that you can mimic a room, you can mimic the walls or how much conductors you have, and you can see how the signal is propagating in that very large area or through space, right? So those are applications from the top level. Please do all this, making sure you have the power. Please do this cost effectively. So we can break it down also saying, okay, those are scenarios that are coming from management. And so they would probably say, yeah, we should have the ANSYS tool test. But now also, us as the engineers, what are we going to do by practice? What tool are we going to use? Are we going to look at all the things that are involved in making a smart device or any device? So whether it's a smart device or whether it's for, power electronics or semiconductors, how do I create these things so that they can be used in some sort of networking or infrastructure? How am I going to create all these smart gadgets so that Verizon or any of the carriers can transmit them? Or if I were Verizon or if I were Alcatel, how do I create that antenna mast? How do I create those filters and those antennas to be placed up on those antenna masts? And then how I collect all that data and look at it and intelligently and quickly so that I can give you instant feedback. So how are we going to do that? Well, we're going to need sensors. We're going to have to look at our communication link. We're going to look at the electronics, at the boards that are in these things. We're going to have to look at, the structural and thermal effects of all these things in this environment, and we're going to need embedded software so that we can look at the data. And so if I broke it down and I look at different scenarios for these arenas, if I look at sensors and communications, right, I've been talking, just antenna design and integration, but I haven't talked about EMI and EMC. And so I had one screenshot there with that was really for heat sinks, right? So we had a lot of we had a board, and we had the computer chassis, and you could see some vents or holes in it. So we have to make sure nowadays, because as we've gone on in time, we now have more regulations that we have to be compliant to. So there's EMI and EMC. How much are we radiating, or how much power is coming in? So we have to be conscious of this, and our tools have whether it's for SAR or if it's for, radiation in the sphere, we have those packaging type of specs that are included in our tools. We could look at MEMS and RFID, right, for sensors. Big thing, right? All these smart devices have some sort of sensor in it, and we are going out, right, the 70, 80 gigahertz zone. So it's all cries out, hey, we need some source of simulation. I don't know if this will work. I don't know, if I change, what I think structurally is a small detail, is that going to matter for me electrically? I got to look at the board, right? I got to look at the power efficiency. I got to look at the power delivery. I have to look at thermal vibration and shock. I have to look at model, right? We want to look at all the variations of our design. We're going to be looking at model-based design and simulation. We're going to say, what if scenarios, right? And so here is just, here's the smart watch here. This actually happens to be the result of, shock and vibration on the front of the watch. It was dropped and it was to show where was this going to shatter, where was the point of failure. So the watch and its elements, and it's very hard to see the circuit board on the front face of the watch here, and the antenna element that's wrapped up in the band itself. So we would look electrically on the design and the antenna design of this device, but we still need to look at it again structurally and mechanically to make sure that when it's in use, it is not going to fail. Here's another scenario. I worked on this one with a couple of my colleagues on the mechanical side, the structural side, and the fluid side. So this was just a design of the smart LED, the smart light. It was for a smart home application. We have all these smart sensors here. And so this one was, you go into, the scenario was, the manufacturer says, I need to make sure that in my design that I can monitor the change in the temperature of the room as someone walks into the room, okay? I need to make sure that that light is going to turn on. Please make sure all that electronics is in there. Please make sure that we are going to monitor the light that is coming out, the heat that the smart bulb is radiating out, so that I don't burn up the boards or the electronics that are in the LED. So form and function, the outside of this, the head of this, the neck of this, has to be by the standard LEDs, right, the light bulbs, because we're just going to say, I'm going to take this light bulb and I'm just going to put it up in all of these existing features. But I want to include all the smarts in it because the market demands that it needs to not only know GPS, right, it's going to need to know, it needs a sensor in there for temperature, and it's going to go and be able to have an antenna on it so we can tell the controller, please turn me on. Okay, so this was a very non-trivial simulation that we had to do, pulling all our physics together, and we used a platform that we call Workbench. We brought in the geometry. We had to design the antenna element. We used the HFSS design. We had to be cognizant of how the air was flowing, right, inside the unit, inside the housing of that light bulb, as well as the airflow that was in the room that it was placed in, okay? Because not every room is air conditioned, right? It's not, or it could be heated up, and there's different environments. We have to be cognizant of airflow, or even location, because this actually happens to be in an industrial application, and so there was an HVAC system that was there. So there's also noise and vibration that is included. So we have to be cognizant of the electrical side of things, but we also need to know what the temperature or the gradient of the temperature on the outside in conjunction with the temperature that is being caused by all the electronics that are on the board. And so this is a way that we can simulate your scenario here or your customer scenario. Okay, let's see. And so again, in one of the first slides I showed you, we have a manufacturing floor here. Nothing stops us to look at what the radiation pattern or what is being radiated out onto someone who is walking the manufacturing floor. So we can do some virtual prototyping there. We can probably, unfortunately, we have all these devices that monitors us, so we can collect all the data, or whether the environment is, within a car. So we span, simulations from components, from physically small parts into very large, physically large platforms. Okay. And just by the way, we do have more than the male model. We have several different human body types. We have and different sizes. There's male, female, and there's child. There's pregnant. So there's standing, sitting, laying down. So we do have human body parts that we can offer to you to use with our simulation tools. Let's see. All the information on there. And so this is a slide I started, so I just wanted to emphasize again, and I know I've repeated it, that we're here at ANSYS, we're a simulation house. We can help you with your simulations from the component side, up to the packaging side, up to very large systems. Systems can be including, inert parts, different human body parts. It could be underwater. Different scenarios for you to test. So we have aligned our products and our product features to the needs of the trends or the initiatives of different industrial areas. So I was focusing on smart devices, because you can easily put that not only smart devices, your power electronics, if you're looking at other energy resources, if you're looking at renewable energy. These things can also be included if you're looking at the transportation arena. So this is just a specific case of an industry application of our tools. And so with that, I will hand it over back to Tony.
Thank you very much, Charlotte. So, this is the commercial part of the presentation. Mentioned earlier that this presentation was brought to you by ANSYS Incorporated and CAE Associates. I just want to give you 2 or 3 slides on who we are and the services that we can provide. So, as I think you've ascertained from Charlotte's presentation, ANSYS is the leader in simulation software. ANSYS is $1 billion in revenue, and as Charlotte presented throughout the presentation, that we have a wide range of physics that we use in the simulation area: fluids, structures, electromagnetics, thermal, power integrity, systems, and the embedded software. The power of ANSYS is the ability to couple all these physics together and integrate them all together in a single model. So from an industry standpoint, as you probably have ascertained, the product is very broad-based. So we are in just about every industry that you can think of: automotive, aerospace, construction, electronics, healthcare. We're working with all the leading companies in all these various industries. Again, I mentioned ANSYS is $1 billion in revenue. We're global. ANSYS is throughout the world. 1,300 people throughout the world. 45,000 customers globally. So far-reaching from here in the U.S. Throughout the entire world. And it's the ability of ANSYS to couple and to integrate all the physics together under a single model that allows the software to simulate real-world conditions, and that allows our customers to predict with confidence that their products are going to work in the real world. And I think that's, Charlotte presented a lot of those scenarios very well. So that's a little bit about ANSYS. CAE Associates, we are the local channel partner for ANSYS. So we service customers from Philadelphia all the way up to Boston. We started out as a channel partner back in 1985, so we've been doing this for more than 30 years now. What we like to say is ANSYS provides the software and we provide everything else. We basically, in that territory from Philadelphia to Boston, we sell the ANSYS software suite. We are the first line of technical support for all the customers in that area. We provide training. Anyone who buys the software, we provide training to get up and running as an introductory level and also as advanced topics along the way. You know, a lot of what we do is also consulting service. Customers might not have the bandwidth in-house, the man-hours to do the analysis, and then we can do the analysis for you on a consulting basis. Or it might be an area that you don't have a lot of experience with and you really need an expert in the field. And that's what we are. We are the experts in the field in all of this. So really, we work with our customers in any way that makes sense for them to reach the design goals and for them to realize the return on investment if they purchase the software. So that's how ANSYS and CAE Associates works together to ensure that you achieve your simulation. So that's us. You've heard from Charlotte. I'm Tony. I'm the Regional Sales Manager for CAE Associates. This is Chris Messelbach. He's our lead electrical engineer, senior project manager at CAE Associates. If you have any